All right, let's dive in. Today, we're going to talk about something really powerful, a whole new way of thinking, really. It's a framework that lets us formally update what we believe when we see new evidence. We are, of course, talking about the Bayes approach.
And it all kind of boils down to this one huge question. How do we get better at being right? I mean, it's something we all want, right? But what if I told you there's an actual mathematical way to think about learning, a way to get better at refining our own beliefs?
And that right there is where Bayesian inference comes into play. You know, at its heart, it's just a method for updating what we know. So you start with some initial belief, we call that a prior, then you go out and see some new data. And the new belief you form after seeing that data, that's your posterior. It's literally a mathematical way to change your mind. How cool is that?
Okay, so what makes this so different? Well, it's really interesting when you compare it to the classical way of doing things, the frequentist approach. A frequentist looks at a ton of data and asks, okay, assuming my idea is true, how likely is it that I'd see this data? But a Bayesian, they flip the script entirely. They look at the data and ask, all right, now that I've seen this new evidence, how likely is my original idea? It seems like a small change, but trust me, it's a massive, massive shift in how you see the world.
So here's the game plan for today. We're going to start with the power of prior beliefs. Then we'll see how we learn from data. After that, we'll jump into how to model a complex world with this stuff. And finally, we'll figure out how to choose the best model. Sound good? Let's do it. All right, first up, the power of prior beliefs. This is the bedrock, the starting line for any Bayesian analysis. So the big question is, where do these priors, these starting beliefs, actually come from?
Yeah, so a prior isn't just pulling a number out of thin air. It's not a wild guess. There are actually structured ways to come up with them. You could, for instance, ask an expert for their opinion. Or sometimes you pick one just because the math works out nicely. And then there's this really cool idea called a non-informative prior, which is basically designed to be as neutral as possible to really let the data do all the talking.
But this whole idea of subjective beliefs brings up a really important question, right? How good are our own gut feelings? Especially when we're really, really confident about something. Are our built-in priors actually tuned to reality?
And this is a perfect example. Check this out. It's a study of weather forecasters back in the 70s. And what they found was that these forecasters were amazing, but they were also consistently just a little bit overconfident. So when they said there was an 80% chance of rain, in reality, it only rained about 75% of those times. It just goes to show even the priors from the absolute experts need to be nudged and corrected by cold, hard data. Okay, so if even the experts need to adjust their beliefs, how do we actually do it? Well, that brings us to the engine room of this whole approach, learning from data. And here it is. This is the heart and soul of the whole thing, Bayes' theorem. Now, I know the formula might look a little scary, but the idea is actually super intuitive. It just says that your new belief, that's the posterior, is a combination of two things. First, the likelihood, which is just how well the new data fits your belief. And second, your old belief, the prior. You just multiply them together. So you see, the new data doesn't just wipe out what you thought before, it updates it, it refines it. Your new understanding is literally a mix of what you knew and what you just learned.
And this isn't just a one-and-done deal. Oh no, it's a cycle. It's continuous. The posterior belief you end up with after seeing some data, that becomes your new prior for the next piece of evidence that comes along. It's basically a recipe for lifelong learning encoded in math.
But here's where it gets really powerful. This whole cycle isn't just for simple coin flips. I mean, the real world is messy, right? It's complicated. Data is often nested inside other data, and this is where Bayesian thinking really, really shines, especially with something called hierarchical models.
Okay, let's build this idea up from the ground up. So imagine we want to understand a student's test score. That's our starting point, the individual student.
But hang on, that student isn't just floating in a vacuum, right? They're in a specific class, and that class has its own teacher, its own group of students. It's a whole environment.
And then you zoom out again. That class is inside a particular school, and that school has its own funding, its own policies, its own location. You see what's happening? We have these layers, this nested structure, student, inside a class, inside a school. And that is exactly what a hierarchical model is built to handle. It just copies that real-world structure. So, a student's score is connected to their class average, and the class average is connected to the school's average. But here's the real magic.
The model lets information flow up and down between these levels. So, what we learn about the school as a whole can actually help us make a smarter guess about a specific class, which is super useful if, say, that class only has a few students in it. It's like the different levels are borrowing strength from each other.
Okay, so building these fancy models is great. But what if you have a few different ones? How do you know which one is actually any good? We need a way to compare them, to pick the one that actually does the best job of explaining the world.
Enter a fantastic tool for this job, the Watanabe Akaike Information Criterion. Yeah, it's a mouthful, so let's just call it WAIC. You can think of WAIC as a scorecard for your model. It basically gives you a grade on how well your model is likely to predict future data it's never seen before. But, and this is key, it also slaps you with a penalty for being too complicated. So, with WAIC, the goal is simple. A lower score is a better model.
Let's make this real. Here's data from a study on HIV/AIDS treatments. The researchers tried out a few different models, from the really complex ones at the top to the simplest one down at the bottom. Now, that WAC column, that's our scorecard. Remember, lower is better. And that PWAC column, think of that as the complexity penalty. Now, just look at what happened. The simplest model, the one with the least complexity, has the best WAC score, and not just by a little, but by a lot. It's such a great example of that old idea. Sometimes, the best explanation really is the simplest one.
And this really gets at a core difference in philosophy, which is captured perfectly in this quote from Harold Jeffries. He's taking a shot at the classic p-value here. He's saying, isn't it a bit weird that we might reject a good idea because it didn't predict a bunch of stuff that never even happened? The Bayesian way is totally different. It focuses only on the data you actually have, the evidence you can actually see.
So, this leaves us with a pretty deep question to chew on, doesn't it? If this whole way of thinking is right, if all our beliefs are just probabilities, somewhere between 0 and 1, that are always shifting with new evidence, can we ever be truly 100% certain about anything? Or is knowing something just another way of saying we have a really, really high probability, one that's always open to change?